Hello all, I welcome you all to the 20th lecture and the last lecture in optical properties of solids. So today we will have the final touch on experimental details of electromagnetic interactions with solids, and we will finish with a small introduction to excitons. One must realize that these topics are courses in itself, so we might touch upon a few things but not uh, extensively explore. Okay, so before we go, we treated electromagnetics in two aspects. One is the macroscopic aspect, macroscopic electrodynamics, and the microscopic one. In the macroscopic one, that is in the sense you do not look at how individual electrons work, but you talk about some collectives, right? In the microscopic one, obviously it has to do with classical treatment, and the most commonly used Maxwell's equation, del dot B, there is no divergence. You have del cross E is minus dou B by dou T, and the solution for this is you assume that there exists some vector potentials, and you come up with solutions for let's say the other ones. Del cross B is mu naught epsilon naught dou E by dou T plus mu naught I. If there is current, basically it's J, right? And if you assume Coulomb gauge, you put one in the other, finally you get this equation. Del square E will turn out to be mu naught epsilon naught dou square E by dou T square plus sigma mu naught dou E by dou T. So this is the consequence of assuming a Coulomb's gauge. And here I go through all these things because there is something very important that we defined, what is called as a dielectric function. We got epsilon, which was written as epsilon naught plus sigma mu naught sigma mu naught by omega. So basically this is a complex function, and sigma being the conductivity, mu being the magnetic permeability, and omega being the frequency. So this dielectric function is a function of the frequency of the light, and the epsilon naught is obviously the electric permittivity of the free space, right? And from this dielectric function, obviously we defined two important consequences. One is we defined what is refractive index, which was written as, so basically this can be written as epsilon prime plus I epsilon double prime, epsilon prime being the real part, epsilon double prime being the imaginary part. You can write this as epsilon prime is nr, the refractive index, real part of the refractive index square, minus nr double prime square, and epsilon double prime is 2nr prime nr double prime. One has to differentiate between the dielectric function and the refractive index, and it is the refractive index which finally determines the reflectance in a material, and the reflectance and the absorbance are the two factors which can be experimentally accessible in a material, right? So we will soon see how to use these things. It is in this today's treatment we will see experimentally measured absorbance in different materials, in metals, semiconductors and such, and how do we correlate it with material properties. So this is something that I wanted to bring about because we will talk about these macroscopic aspects today. The thing that I want to also remind you is the microscopic treatment that we did in the previous lecture. So in the microscopic treatment we showed that the Hamiltonian of the electron can be written as the unperturbed Hamiltonian plus from small perturbation H prime, and we showed H prime can be written as E by M A dot P, P being the momentum operator, A being the vector potential as we described previously. And because this is perturbatively treated, we approached this problem with the time dependent perturbation theory, and then we showed that the wave functions after perturbation at any time can be written as summation of some coefficient times the normal unperturbed eigenfunctions, right? So these are some things that we saw previously, and we found that Cn of t can be written as minus I by h cross and some integral 0 to t and some overlap integrals. I'm not going to write those details, but eventually for a very simplistic case of two states, we found that the transition probability from initial to the final state, which can be written by the magnitude of this coefficient square, which tells you what is the probability that the final state psi of t is in that particular eigenfunction, right? So Cn of t square will give you what is the probability. Instead of n, it has to be f, right? Initially it was in Ci and now it turned out to be Cf. What is the probability to be in Cf is Cf square, which was found to be 4 some constant. Okay, I think these constants are something which I probably did not take a lot of care, so one has to look carefully what these constants should be, but this is what I got last time. Sine square omega naught minus omega into t by 2 by omega naught minus omega square. So this is sinc square. Sinc square, as we saw previously, if t tending to infinity, can be represented by a delta function, and this equation probably gives you, or not probably, gives you the energy conservation in a scattering problem. So in the sense that if you take an electron in E naught, for it to be scattered in Ei, it has to undergo this energy conservation, which is delta E naught minus Ei plus or minus h cross omega, omega being the frequency of radiation. So what it means, if I have some two states, final and the initial state, we saw that the electron can be excited by a h cross omega to directly up, or an electron which is already excited can come down between the initial and the final states to give you a photon. And when it gives out a photon, then note this photon is phase coherent with the initial photon, so you can have what is called as a stimulated emission. The first one, where an electron initial state or in the valence band went up, is called as an absorption. We saw one funny case where there is no photon, but it still stimulates an emission from the excited state to the bottom state, which is called as spontaneous emission. It is to do with the vacuum fluctuation in the zero photonic state, right? In the photonic vacuum also, it has some energy. It does not have zero energy. It has half h cross omega, and that vacuum oscillations gives you this spontaneous emission from an excited state to the ground state, right? So in this, we showed that there exists some energy selection criteria. Given an initial state, you know what final state it will choose, because the summation should add up to the photon energy. But most often in our previous treatments, we also came up with another condition, right? We saw that if you have an electron in the state k, and and the final state has a wave vector k prime, right? We also said that k plus or minus q should give you k prime, q being the wave vector of the photon, right? So it also has to conserve momentum. This is what we saw, right? This is what finally told you that only direct band gap semiconductors are optically more active. So one can always question, in our previous treatment, why didn't we get anything which relates to the wave vector conservation? Let's deal with that very quickly and come back to our original treatment, right? We will show that excitation using electromagnetic radiations should also satisfy the wave vector conservation in addition to the energy conservation. Obviously the trick lies in S square, because that is one thing which we have not used. So to refresh your memory, S or S square basically is this, right? So final state A dot P initial state, right? So this was A dot P comes from the interaction Hamiltonian. So basically it is an overlap integral from the initial and the final state. We can take the initial and final state to be block states. So let's take the initial state to be some ui e power I k I dot r. The final state we take as uk e power I k f dot r, not k, sorry, it has to be uf, right? Final. Given these two, let's substitute into this S square. Mod S square is basically uf star e power minus I kf dot r, instead of, I am already expanding this, right? So it has to be an integral. This has to be over all these spaces into A. This A I am writing as let's say I write A dot P, and the final is ui e power I k I dot r dr. And obviously this A can be written as E uf star e power minus I kf dot r, and as we saw previously, this can be A can be written as some E naught e power I k, instead of writing k here, I am going to write q, just to differentiate it from the electron, q dot r minus omega t into dot p into e power I k I dot r into ui dr, right? Obviously the omega t is a time part which we have to take out, right? Because it was already considered previously, which will turn out to be E naught, the entire thing square. We're talking about the square, so E naught can be taken out, E naught into E by m, which is considered previously, integral uf star e power minus I plus I q minus kf dot r, right, into P acting on e power I k I dot r ui dr, right? And this P acting on ui e power I k dot r has to be expanded. So P acting, P basically is a differential, right? So you have to use the product rule. Ui e power I k I dot r can be written as ui into P acting on I k dot r will give you I k into e power I k I dot r plus e power I k I dot r into P acting on ui. This is something that you don't know, right? So this is this product. I have to substitute this into this, which will give me E naught square integral over all spaces minus infinity plus infinity. I write one integral, basically it has to be three integral, right? Full spatial integral dr is dx dy dz, but I'm just simplifying here. So UF star e power I q minus kf dot r into summation ui into iki e power iki dot r plus e power iki dot r into pui. Right? Remember, UF multiplied by UI. UF is the final state potential function, and UI is the initial state potential function. So what it means is these are all solutions for the same Hamiltonian. So UF star UI will be 0 because this is the initial state and this is the final state of the same Hamiltonian. They are going to be orthonormal. So this will turn out to be 0. This one will not turn out to be 0 because it is P acting on UI. Right? So it will finally lead to only one term here, which will be integral minus infinity to infinity UF star into e power I q minus kf from here plus ki dot r into pui dr. And remember, this is summation over all spaces, so you can divide this into lattice spacing and the deviation from the lattice point, right? So basically this can be written as E naught square summation over all lattice spaces. So what I'm saying is this small r can be written as capital R some lattice space plus r prime, that is the deviation from the lattice point, right? So summation over all r e power I q minus kf plus ki dot capital R multiplied by the summation over in the unit cell only uf star e power I q minus kf plus ki r prime p ui dr prime, right? And this summation over all lattice spaces is basically inverse Fourier, right, of a constant value. So this will turn out to be a Dirac delta function. So it will be E naught square into Dirac delta of q minus kf plus ki multiplied by unit cell summation of uf star, and this because this is a Dirac delta function, this exponential will turn out to be 1 into p ui dr prime, and this integral, of course, I'm going to replace it by just pfi, which will turn out to be E naught square pfi square into delta square of q minus kf plus ki. This is a square. So basically the scattering will be non-zero only if q equal to kf minus ki, and this is we have considered only for positive a, and once we consider the fact that there can also be the complex conjugate, you will get q can also be equal to kf sorry, maybe I should write it in a different way just for ease of k final is k initial plus or minus q, q being the wave vector of the photon, right? So this is momentum conservation, which also has to be conserved when you have an interaction with an electron, and this is what finally gives you intra-band and inter-band scattering phenomena. So basically, if you have a semiconductor like this, an electron from here can be excited only to places which are very close, such that this separation in K space can only be Q at max. And this Q is very small because photonic wave vectors are much smaller in comparison to the electronic wave vectors, right? So this is, let's say this is Ki and this I is Kf. So this kind of transition is called as interband transition. If you have an electron or an electron here, it gets scattered to another Kf here. It is only possible if it is added by Q, right? So this kind of a scattering is called as intra-band transitions. This can be one sort of intra-band. You can have another transition like this. Obviously it cannot be, if this extension cannot be too much, because the Q value should be small for all these kind of transitions, right? So with this, let us go take a look at some commonly observed experimentally measured properties of metals and semiconductors, and from there let us look at where we started and where we are currently. So this is a measure of reflectance of different metals, and we saw previously that the reflectance is a function of the real part of the refractive index of the material N, right? And when we see that all metals do not have very simple and straight features across various wavelengths, and as we saw previously, N or the dielectric or the refractive index, refractive index is also a function of the frequency or the wavelength of the light, right? And you see that there are some distinctive features. Let's say for copper has almost flat lines at long wavelengths, and close to, let's say, about 600, there is a small dip in the reflectance. This reflectance also shows that it will have a small dip in the real part of the refractive index, and you know the real part of the refractive index and the complex part of the refractive index are linked together by Kramer-Kronig relation, right? So if there is a dip in the real part of the refractive index, if you do the Kramer-Kronig relation, it will show that there will be a small peak. So if I plot K, or the absorbance or the attenuation in the material, you will have something, let's say for copper, you will have a small peak here which give you a dip, right? So one has to understand why does this happen. To do this, we have to once again go back to our treatment and then see how do we reconcile with our measurements of reflectivity of metals. Why do metals reflect so much, right? And why don't semiconductors reflect? What happens? What's the difference, right? For that, very quickly we are going to deal with what is called as the Drude model of optical conductivity. This is a slight deviation from what we have been talking till now, because once again we are now going back to the macroscopic behavior, but this is something which is important because this explains a lot of aspects in optics with metals, because we are basically talking with solids. With semiconductors, all these aspects are true. The microscopic origin is very good, but for metals the microscopic origin does not give you a lot of information, but the macroscopic origin or the macroscopic treatment gives you some information about conductivity or electromagnetic interactions under various frequencies, right? So for that, let's go back to our original Drude's equation of changes, let's say we assume there are free electrons, right? Electrons are free, they scatter with themselves as well as ions. And under this and all the assumptions of Drude's model, we saw that if there exists some force, now we are going to assume a time dependent force. Okay, this E, the force is E of t. You have some electric field which is time dependent, because we're talking about electromagnetic radiations which are oscillating in time, right? Under such situations, the momentum of the electron gets modified by the electric field that you are given minus p of t by tau, and tau is the mean lifetime, right? So this is the acceleration of the momentum, and you have some deceleration or some scattering which reduces acceleration, which gives you some finite velocity. If you do not know from where this comes, I recommend you to go back to our Drude statement. We will see where this comes from, right? And the easiest solution for this, given that E of t is some E of omega into e power minus I omega t, omega being the frequency of the electromagnetic radiation, the simplest equation solution for this is P of t is some P of omega e power minus omega t. I substitute this, I will get minus I omega P of omega into e power minus I omega t is equal to minus E of omega e power minus I omega t minus P of omega e power minus I omega t by tau. And we do something which we have done previously. We define the current, which is also frequency dependent, as minus En, the momentum by mass, right? So basically EP by m, P by m is the velocity, ENV is the current, right? The charge times the velocity times the number of carriers will give you the current. If this being true, I can get J of omega from the previous expression will turn out to be Ne square tau by m into E of omega by 1 minus I omega tau. Using these two equations, this can be easily obtained. And the conductivity or the complex conductivity under an alternating electric field is now given by some, let's say, sigma prime plus I sigma double prime, where sigma prime is sigma naught 1 plus omega square tau square, and sigma double prime is sigma naught omega tau by 1 plus omega square tau square, where sigma naught is the DC conductivity that we all know, Ne square tau by m, right? So basically the conductivity of a material under electromagnetic radiations is a complex value, and it has this real and imaginary part. If we know that tau is not, basically if there are some scattering, and let's say we know the typical values of tau to be about 10 femtoseconds, which is about 10 power minus 14 seconds, under these situations we know that if the frequency of the excitation or the electromagnetic radiation, if omega is small, then sigma prime is much larger than sigma double prime. Why? Omega is small, so this omega is in numerator here, so obviously sigma double prime will be smaller. Here omega is in the bottom, right? So obviously sigma prime will be much larger than sigma. So your conductivity will largely remain constant, and it will be resistive, so there will be some losses and such. So for small frequencies, starting from DC to all the way, so here it's easy to see, if you put omega to be 0, that is a DC frequency, you get sigma naught. And frequencies till RF and all such of frequencies, you have the metal acting resistively with only a real part in the conductivity. For small frequencies, the conductivity is real. And for very high frequencies, like let's say omega is much larger than typical RF signal. So basically omega, or the frequency, is in um, infrared to visible to ultraviolet radiations. So basically remember, these things are like several thousand terahertz, right? So it's megahertz and above. Sorry, several, not megahertz, it's several thousands of terahertz, right? So these optical radiations are much higher than the typical RF frequencies where we talk about. Under these situations, the conductivity is purely imaginary. Right? So once again, if you go back to this term, omega is extremely large, so the real part comes to 0 here, and the imaginary part here, it's easy to see. So what happens, your omega, so if omega is really large, so you will have the imaginary part to be 1 by omega, right? So basically higher the frequency, even the imaginary part turns out to be 0. So under these situations, there are no losses in the material, and the metal turns to be completely transparent. To the radiation. So there can be some electromagnetic radiations which are completely transparent, like the metal will act like glasses to some radiations. Is it true? Are there any radiations for which the metals is completely transparent? This is the downside of the Drude's model once again. So we will see that there will always be interband interband excitations because of frequencies which are much higher, right? Even in metals you will have interband excitation. So we will see soon enough the band structures of various metals, where we will see intraband scattering and interband scattering, which will show that metals do not turn to be transparent at any frequency. But the Drude's model shows that above a certain frequency, the metal should turn transparent like glass. Now that we have calculated the conductivity, let's go back. We know that the dielectric function was written as epsilon naught plus I mu sigma by omega, right? In our previous macroscopic definition, so here we defined our epsilon, right, which is a function of omega. So if I put that, I put the sigma from our previous expressions, I get a frequency dependent dielectric function, which is epsilon naught minus sigma naught mu naught tau by 1 plus omega square tau square plus I mu naught sigma naught by omega into 1 plus omega square plus tau square. So once again, you have a real and the imaginary part of the dielectric function. And similarly, as we did previously, if omega is small and omega tau is very much lesser than 1, under these situations, it's easy to see that, let's say, so here this omega is very small, right? So the dielectric function turns out to be completely imaginary. So for metals at low frequency excitations, the dielectric function is completely imaginary, and under such situations, n equal to k will be mu naught sigma naught by 2 omega, and the absorption coefficient alpha will turn out to be 4 pi k by lambda. This is the constant thing, and you can substitute this to know what will be the attenuation constant, and it can be seen that the skin depth That is, I have a metal, and over the metal I have some electromagnetic radiations with particular frequency omega. The electromagnetic radiations will only penetrate to a certain distance. It will die, the intensity will die to 1 by E value in a depth which is called as the skin depth. And the skin depth lambda typically turns out to be about 100 micrometer for omega as small as 10 power 7 hertz. And higher the frequency, it's easier to see that the skin depth decreases even further, right? Now at very high frequency, such that omega tau is much larger than 1, then epsilon turns out to be purely real, which will be epsilon naught minus sigma naught mu naught tau by 1 plus omega square tau square, which can be written as 1 minus omega p square by omega, where omega p is 4 pi n e square by epsilon naught m. This frequency is called as plasma frequency, and under this frequency the dielectric constant function turns 0. In the sense, let's say if I plot the dielectric function as a part of frequency, of course under frequencies which are very large, not at very small frequency, right? So we're talking about infrared radiations and above, infrared to visible to ultraviolet. In such radiations, the dielectric function will change from a negative value to a positive value and will cross the 0 at omega equal to omega p, which is called as the plasma frequency. And if epsilon turns out to be 0, right, and we know that epsilon and the refractive index n are closely related, the reflectivity of metal is almost 1 till epsilon is negative, right? And at omega is equal to omega naught, the reflectivity drops to 0. And this discontinuous drop to 0 at omega is equal to omega p is experimentally observed in many places. This frequency is called as plasma frequency, and the reflectivity will again regain back once it goes above, right? So these are experimental facts which can be extracted from the very simple classical Drude's model of optical conductivity. It is also instructive to just, let's say, know the plasma frequency, which is given in 10 power 16 hertz for metals like lithium, sodium, potassium, rubidium. These are all alkaline earth metals, which is about 1.22 in 10 power 16 hertz, 0.89 hertz for this. For potassium it turns to be 0.59, and the corresponding wavelength in angstroms. Okay, let me write in meters, right? So nanometers, which is pretty well known. 155 nanometers for lithium, 210 nanometers for sodium, 350 nanometers for potassium, and 340 nanometers for rubidium. What is the wavelength of green light? Is about 532 nanometers. So it's easy to see that these plasma frequencies are with wavelengths are very close to the wavelengths that we are talking, right? So what we are trying to say is, if I take let's say potassium metal till frequencies which are 315 nanometers, you will have complete reflection. And after 315 nanometers, at 350 nanometers, the reflectivity completely drops to 0, and you can let's say, and you can go shorter. In nanometers, we're talking inverse, right? So you can go shorter and the reflectivity will regain. Right? Alright, so now let's get back to some measured values of electromagnetic interaction with metals. So the first thing we are going to see is a plot of real part of conductivity versus various frequencies. As we saw previously, the real part of conductivity is sigma naught, the DC conductivity, by 1 plus omega square tau square. And if we assume tau to be independent of frequency, now it's easy to see that as frequency increases, your real part of the conductivity should keep dropping, right? And as expected from the very simple Drude model, the conductivity, real part of the conductivity keeps dropping. This is for alkali metals, right? So sodium, potassium, rubidium, all of them have decreasing real part of the conductivity as the excitation frequency increases. But quite interestingly, what happens, like after a certain frequency, you have the conductivity going through a bump, right? This happens for sodium, this happens for rubidium, and this also happens for potassium. So why does it happen, right? So the real part deduced from reflective measurements in 3 alkali metals. So the reason behind this is because of interband excitations. So what happens as we increase the frequency, this equation comes from the Drude's model, right? And the Drude's model do not assume to have existence of bands. There is no Fermi-Dirac distribution and so on and so forth. And throughout this course, we saw that there are always bands and there are gaps. There is a gap in the density of states. There is some states till which at 0 Kelvin things are filled and above which there are empty. And when there are empty and filled states, then our previous microscopic treatments come into play, right? So here I am plotting, let's say, so this is the band structure of copper, this is the band structure of silver, right? For band structure of copper, it's easy to see. So let's say this is the Fermi level till 0 Kelvin. At 0 Kelvin, all these states are filled, right? All these energy levels are filled. Now if I apply some let's say electromagnetic radiation, it's easy to see that an electron at this energy level can jump up, an electron at this energy level can jump up, right? Electron at this energy level can jump to this point as well. Similarly, an electron here can jump up and so on, right? So there are specific energy levels where the absorption, and absorption is typically given by epsilon 2, as we saw previously. Epsilon 2, the imaginary part of the dielectric function, has to do with absorption, right? And the absorption will support specific peaks. You have one peak here, you have another peak here, which corresponds to A and B, and these things corresponds to this jumps on electrical strings. So even in complete metals, you have absorption peaks occurring from transitions, not let's say having from interband transitions. There is not necessarily a gap in the density of states. You can see that there is continuous density of states in copper, but even then you have interband transitions. That is, an electron in one band can jump to another band, right? This is too high, which does not happen, but you have electron from this band jump to this band, having this specific peaks in the absorption. As we saw previously, your epsilon 2 reduces and then it has peaks in absorption corresponding to the gaps in the band structure. Similarly, for silver, you do not have double peak structure, but then you have a single peak at around 4 eV. Where do you have 4 eV? So you can see the topmost band here. Let's say this is your Fermi level. Let's say topmost band here, and you have almost a flat line here from about this gap is about 4 electron volt. So you have a very strong peak at around 4 electron volts, where you have an electron from one band jump to the another band. These are called as intra-band excitations. While these things are observed in metals, in semiconductors this is even more prominent. right? Let's take for instance indium phosphide, gallium phosphide, and gallium arsenide. The absorption coefficient, once again this is epsilon 2, or can also be proportional to k. Both of these things are interchangeable. You can see that these things are 0 for wavelengths larger than 1 micron, and then you have a sharp increase in the absorption value as the electromagnetic radiations have wavelengths smaller than this value, or energy is larger than. So basically, if you have an electron here, you have energy values larger than this, you have an interband transition from here to here, which is seen in the absorption coefficient measurements. One can also understand why silicon is band structure is smoother, or silicon absorption coefficient changes gradually, whereas indium phosphide, gallium arsenide, gallium phosphide, indium gallium arsenide, all of them have very sharp rises. Can you think why this is to be true? It has to do with the direct band gap and indirect band gap and all such factors, right? And this is the famous Fermi golden rule, as we derived. The scattering probability, that is omega ki, is proportional to 2 pi by h cross all the available states. The overlap between the two states, h cross is a dot p. This is the valence band, this is the conduction band, and the mod of this overlap square, and this delta ensures that there is energy conservation. And when you expand this overlap, it will ensure that there is wave vector or k value conservation as well, right? And it is not just this, the overall scattering rate also depends upon the occupational probability. F of v, let's say scattering from bottom band to the topmost band is proportional to the occupancy of the valence band and the emptiness of the conduction band, right? So the scattering rate from bottom to up is also determined by the occupancy of the valence band, how many states are filled, and how many states in the valence band, in the conduction band, are empty. The product of these two tell you the probability, scattering probability, or the transition rate from the valence band to the conduction band. This is obviously true from the various descriptions or definitions that we have read during our treatments of scattering in Boltzmann transport equation and so on and so forth, right? There is one aspect of things that we have not discussed till now is nanostructures. So in semiconductors, we previously saw that you can fabricate a lot of nanostructures. Starting from gallium arsenide, you have let's say aluminum gallium arsenide, and then once again gallium arsenide and aluminum gallium arsenide. Let's say this is gallium arsenide. This will give you the kind of quantum well that we are talking here, right? So basically you have Al gas here, gas here, and repeated structures of this will give you a superlattice, but here we are just talking about one. And whenever we are having quantum wells, obviously the states here are confined, and we saw previously, irrespective of the depth of this well, you will always have at least one. Deeper ones will have much larger, and the wider ones will have continuous states depending upon the width and the height of this well. The states will change. We have seen this previously in your homeworks as well as in our descriptions, right? So because you have discrete states in the valence and in the conduction band, you will see discrete peaks in the transmission and respectively the absorption as well, right? So here I am plotting the transmission. So what happens is I have some stack like this, and through this let's say I put some light electromagnetic radiations, right? And I measure what got transmitted through. Assuming this gas is too small, I'm going to just measure what got transmitted through at this point. And here you will see that I will have this peak positions corresponding to various conduction and valence bands. So here 1 1 2 2 means the first conduction band and the first valence band, 2 2 means the first conduction and first valence, second conduction and second valence, 3 3 is third conduction and third valence, and so on and so forth. right? So here you have electrons, the conduction band, and light hole. Here I have electrons and conduction in the and heavy holes. These two are not clearly separable, because the heavy hole and light hole energy levels are too small in comparison to this huge energy range that we have here. There can be situations when the heavy hole and the light hole bands are significantly separated in comparison to the band gap. Then you will start seeing discrete features here corresponding to the heavy holes and the light hole bands. But the important thing that needs to be noted is that when you have a quantum well, you will have transmission and absorption peaks which are very well separated, and which can be used to identify some sort of a material that you have. Eventually, a quantum well can also be used as a very fine, let's say fine line width emitter, which is used in lasers and so forth, but we will not go into those details right now. But one just needs to understand the use for a quantum well in optoelectronic applications is particularly to, instead of having a broad electroluminescence spectrum, let's say like this, a broad absorption spectrum. Let's say InGaAs has a very broad absorption spectrum as shown here, right? If you have an InGaAs quantum well, what we will have something like this. The absorption will go through oscillations, and these oscillations will correspond, the width and the separation of the oscillations will be determined by the width of these quantum wells, right? Now, in addition to these interesting aspects, there is one other thing that you need to know. So this is what happens when you lower the temperature. So here I am plotting the absorption intensity for different energies. Clearly at 140, at 14 nanometer wide well, you clearly have very well separated emission peaks. At 210 or 21 nanometer well, you have more number of peaks, right, within the same energy level. And at around 400 nanometers, the peaks are now not very well observable, and you have almost a continuous line, which is typically seen when you are already close to a bulk. This is 400 nanometers. However, one interesting aspect you see is an emergence of a very sharp peak even before the onset of this let's say excitation, the absorption peak. Why do you see this? This was observed at very low temperatures. Why do you see this? So this is the last this is the aspect of the last discussion that we will do regarding optical transitions, and which is excitons. Right. So excitons are basically bound electron hole pairs. We will soon see its theoretical formulation. So what do we mean by bound electron hole pairs? Is that, let's say if we have a conduction and valence band like this, and you have an electron in the valence band which got excited to the conduction band here, right? Loss of an electron gives you some sort of a positive charge here, and then a conduction band has a negative electron here having some sort of a Coulombic interaction. And this Coulomb interaction is basically a particle-particle interaction which we have neglected till now. So very soon we will write the Schrodinger equation for a two-body problem. So this will be the first time we are talking about two-body problem. Till now we were always been talking about a single electron and the potential faced by a single electron. We have always neglected electron-electron interactions, electron-hole interactions, and so on. So from now, this is the first time we are going to talk about an electron interaction, which is an electron hole interaction. Whole electron and the hole is basically a vacancy, right? So basically we are talking about a a completely filled band, an electron and complete interaction between electron and completely filled band. So there are two kinds of exciton which are typically treated. One is an exciton in a semiconductor where you have a lot of free electrons and the Coulomb potentials are screened. So when the Coulomb potentials are screened, you have a weak electron hole interaction which is called as a Barnier type of exciton. You have a Frenkel type of an exciton where you do not have Coulomb screening, you do not have screening from the other free electron carriers that you have here, and you have a very strong electron hole interaction. And when you have a strong electron hole interaction, these energy levels between the first excited state and the ground state are now separated, right? So now you have, instead of these two being the two separate energy levels, now the energy levels are closer. You have, let's say, one of these electron getting scattered up, and this scattered electron has a very strong electron hole interaction, reducing the binding energy, giving you the energy gap which is much smaller than the previous energy gap. This is called as a Frenkel exciton, but which is typically seen in organic materials, which we will not go to for now. We will be talking about Barnier excitons where the Coulomb field is screened by the presence of a lot of free electrons in the conduction and the valence band, right? So let's now write a very small theoretical treatment for excitons, and then we will see how the Barnier kind of excitons can be treated very similar to an hydrogen atom problem. So let's say the Schrodinger equation for excitons in a semiconductor. So what we are talking is, let's say we have a material here, and then you have an electron and a hole having bound by strong Coulomb interaction. Right? And how do we write this? The total Hamiltonian H is the summation of total energy, right? And we write the electron hole wave function as some psi, which is a combined electron hole wave function, right? And let's say you have some origin at some point. Let's say the hole is at R hole and the electron is at R electron, right? Under such situations, the electron energy can be written as the momentum of the electron by twice mass of the electron, right? And the whole Hamiltonian can be written as the whole momentum square by mass of the whole, and the total Hamiltonian is summation of electron energy plus the whole energy plus the Coulomb interaction between the electron and hole, right? So basically it is minus E square by epsilon, that is the dielectric constant of the material, into Re square minus Rh square, right? This is Rh, this is Re, then the vector gap between the two is Re square minus Rh square, correct? This is the total Hamiltonian. And how do we write the Schrodinger's equation? Is Pe square by 2me plus Ph square by 2m whole minus E square by epsilon Re square minus Rh square into psi, which is a function of Re comma Rh, which is given by the energy psi Re comma Rh, right? While this E is the dielectric constant, and we take this dielectric constant to be isotropic one, right? Now to solve this problem, we are going to use the conventional technique which is used always in classical mechanics when you have multiple bodies. What we do, we use what is called as a center of mass, which let us say is not at Re by Rh, but it's say at some point R, right? And these let's say the electron and holes is thought to be basically the movement between the electron holes can be represented by another two variables, is r and r prime, which is r being the center of mass moment and r prime being the relative movement between the electron and hole from the center of mass, right? So now I write r vector is re vector minus rh vector, and the center of mass, this is the r prime that we're talking about, and the center of mass rho is now written as mere plus mhrh by me plus mh. This is the way the center of mass is typically defined. This is basically rho, right? And the total wave function, which is a function of re by rh, is now written or summation of two functions, f, which is a function of the relative displacement r, and g, which is function of rho. Rho is the center of mass, right? So basically this is how this total thing is split. And let's take this equation, and if I write this, I will get p, let's say rho square by twice me plus mh. This is the total center of mass, right? The center of mass now moves with the total mass of electron and the hole, and the momentum of total electron plus hole, plus the individual particle now moves at, this is not rho, this is p r square by 2mr. What is the mass of this relative moments? We will define what this is, minus e square by epsilon r, right? R is the now difference between these two, distance between these two, multiplied by f into g is some, let's say gamma times f into g. Right? This is how the two body Schrodinger equation is now written in the center of mass representation, where 1 by mr is written by 1 by me plus 1 by mh. So this is some sort of a capacitance summation, and this mr will always be smaller than the either of them, right? So this is how this capacitance is typically defined. So now let's say this piece rr, so let's say p is basically momentum, right? And p of rho multiplied by g is going to be 0. So now you can split this into two different equations. One is the center of mass component, which is p rho square by 2 me star plus mh star into g of rho, which will be some constant. This is the eigenvalue g of rho. And the second part, which is p of r square by 2mr minus e square by epsilon r, acting on f, will give me some, let's say some nu times f, and the total energy, this is the gamma that I wrote here, is summation of this plus nu. Now there is something which is important to see. So this center of mass, now it's easy to see, the center of mass now has twice the total mass, but it does not have any additional potential here. So this is almost like a plane wave solution, right? And the relative displacement terms looks like the hydrogen atom problem. right? So basically you have some momentum square minus some spherically symmetric potential, right? E square by epsilon into r. So the exciton is now split into two forms. One, the center of mass motion of the electron hole pair, which behaves almost like an electron in a periodic potential, right? You can have let's say the block wave, because all of these guys are effective masses, right? It seems as if it is in a periodic potential which moves along like a single electron, but now whose mass is summation of these two masses. And the relative motion between the electron hole can now be treated like an hydrogen atom problem. And when you have a hydrogen atom problem, you know how the energy levels are distributed, right? So that is given here. So when you have a valence band and the conduction band, and when you have a very strong electron hole interaction, it acts as if you have exciton energy levels which are like hydrogen atom energy levels. So you have 1s, 2s, and you have, let's say, 2p, then you have 3s, then you will have 3p energy levels, then you have 4s, 4p, 4d, 3d, and all those energy levels like you typically have for hydrogen atom problem. Such kind of excitons are called as Wannier-Mott excitons. Another important thing that one needs to understand when we are talking about excitons is that whenever you have quantum wells, the separation between electrons and holes spatially is severely confined, right? And the severe confinement in the electron and hole positions increases its Coulomb interaction, and hence the excitons in a typical semiconductor material in a quantum well is a much stronger phenomena than excitons in a bulk 3D crystal, right? So excitons in a quantum well is much more important than excitons in a bulk 3D material. There is something that I need to show you before we quit. So let's say, so here you see gallium arsenide at room temperature, you have gallium arsenide at lower and lower temperatures, right? The excitons are bound together by what is called as an exciton bound energy, and the binding energy of an exciton is twice the energy of I should not write twice. It is basically energy of an electron plus energy of a hole minus the energy of the electron hole pair. The energy of the electron hole pair, as we calculated previously, is, let's say, plus nu, right? This difference in energy between an electron and hole being separate and the total energy of the exciton as a pair is called as the binding energy. And when the thermal energy is larger than the electron binding energy, obviously the electrons and holes will no longer be bound and they will be broken, right? So at room temperature, you typically do not have any signatures of excitons. As you go lower and lower in temperature, let's say at about 21 Kelvin, the thermal energy is much smaller than the exciton binding energy, and you will have a strong exciton peak positions under these situations, right? So to just quickly summarize, so today we saw about the macroscopic electromagnetic radiation interactions. We saw that you can use the Drude theory to understand how reflection happens, and in order to completely understand how electromagnetic radiations interacts with metals and semiconductors, you need to look at the microscopic picture. You need to see that you can have intra-band excitations, and when you have intra-band excitation, when you have electrons and holes, there can be a very strong electron hole Coulomb interaction which gives rise to the excitons in a material. The excitons are typically found if the binding energy is higher than the thermal energy. So in most situations one needs to cool a system down to low temperature to start observing any exciton effects. But in the recently identified 2D materials, the exciton binding energies are as high as 250 millielectron volts. For example, in MOS2, the exciton binding energy is about 250 millielectron volts and the thermal energy is 26 millielectron volts. So the exciton binding energy is about 10 times that of thermal energy, right? So you have room temperature stable excitons in 2D materials. Can you see why 2D materials have very high binding energies? One simplest reason is there is an extreme spatial confinement, at least in one direction, right? This extreme spatial confinement brings the electron and hole as close as each other, and hence the Coulomb potential V is E square by 4 pi epsilon into R, right? Because R now seriously reduces, the Coulomb potential is now extraordinarily high, which makes the binding energy much higher, right? That's why 2D materials like MOS2 transition metal dichalcogenates have room temperature stable excitons. There are multiple applications, but we will not go into it for the purpose of this course. So with this, we'll stop our lecture today. Thank you.